Hello, and welcome to our first sort of actual lecture handout. I will try to walk you through this lecture on inverses mod n, and we'll finally see why we've been caring so much about the Euclidean algorithm and Bezout's theorem on reassembly. Since this is the first actual sort of lecture we're going to do together, the previous thing was just an example. This one has some exercises in it for you to do for a grade on Canvas. So as I walk through this document, I'll point out that feature and how you'll do that in Canvas, and this is how you're going to learn the material, is you'll check your understanding by doing these exercises. So recall this notion I laid out in the previous handout, which is when two integers are called relatively prime. So we say this a lot in crypto, but it just means that their GCD is 1. So that's the point here beyond for this first definition, is that two integers a and b are called relatively prime if the GCD is 1, okay? And so what this means, certainly it means they have no common divisors except for 1 by definition, but you should also think of it this way, in that what it really means is that a and b don't share any common primes in their factorizations. So you can factor a into primes, and you can factor b into primes. And if they're relatively prime, it means that they don't share any of those primes. So here's an example, in example 1 here. 12 and 77 are relatively prime, since the GCD of 12 versus 77 is 1. And sure enough, if you factor 12 into primes, you get 2 squared times 3, and 77 into primes is 7 times 11. And 2 and 3 don't have anything to do with 7 and 11, right? All those primes are distinct. And so that's the real reason that 12 and 77 are relatively prime. And this ends up being one of the most important ideas in all of cryptography. You will hear me mention relative primeness throughout the whole rest of the semester when we're discussing modern cryptographic algorithms. They all work based on this idea, okay? So here's the real reason why we care. This is the content of Theorem 1 on your screen. When two integers are relatively prime, like 12 and 77, then one of them is always invertible mod the other. So for instance, 12 has to be invertible mod 77 because they were known to be relatively prime. So that's the content of Theorem 1. A mod n is invertible if and only if the GCD of a and n is 1. And that's why we care, okay? So the things that are going to be invertible mod n are exactly the things that have a GCD of 1 when they are compared to n. I'll prove this at the end of the handout, but for now, let's do some examples, because an amazing thing happens from this. So in class, right before we left, we worked out that the GCD of 209 and 735 is 1. And if you believe my theorem, this means that 209 is now known to be invertible when you work mod 735. All right? So what we're going to do is use what we know about Bezout's theorem and actually work out, well, what is the inverse of 209, right? And I fully understand that you can take your modular calculator, punch in 735 as the modulus, then punch in 209 and ask your calculator to invert it and get the answer. That's cool. But the point of this is we are learning what the calculator is actually doing to do that. The calculator is executing some algorithm to find the inverse of 209, and we are learning what that is, okay? So when we did this example in class, we also reassembled it, right? And since their GCD is 1, then 1 can be reassembled as a multiplier of 209 added or subtracted to a multiplier of 735. And here's what we got. We got that 1 is 60 times 735 minus 211 times 209, right? And there are my two ingredients, 735 and 209, 735 and 209. So now the trick is take this equation and just reduce it mod 735, right? Well, when you reduce this equation mod 735, 735 is 0. So this term is going to drop off. So here's what happens. So 1 is equal to 60 times 735 minus 211 times 209. But 735 is 0. And so this term drops off, and what you get is that 1 is congruent to negative 211 by 209 mod 735. Well, that is exactly the definition of 209 being invertible. There must be somebody else. In this case, we have just learned is negative 211, that when you multiply that somebody else times 209, you get 1. And we just found out who it is. It is negative 211. Now what we should do is reduce this mod 735, because I want an answer that's from 0 to 734. So when I take negative 211 and reduce it, I get 524. So we just learned that the inverse of 209 is actually 524. If you punch that in your calculator, you will see you get 524 as an answer. This is amazing. What you learn is that because of Bezo's theorem, 209 has to be invertible, mod 735. And the inverse, are you ready, is sitting right there. That is the inverse. And all you got to do is reduce that inverse to get rid of the minus sign. That's the content of our second theorem. If you can reassemble 1 as a GCD, and you know the coefficient of the A, then that coefficient of the A is your inverse. You're done. All you got to do is correctly reduce it mod n to alleviate any minus signs. Let's do a few more examples. Example 3. Let me leave theorem 2 on the screen so you can see it. The key is the coefficient of A is the inverse, but you got to reduce it. So in the previous handout on Canvas, we cranked out that the GCD of 28 against 109 is 1, so they're relatively prime. And that means that 28 must be invertible mod 109. Well, we reassembled it in that handout, and we got that 1 was equal to 9 times 109 minus 35 by 28. Use the fact. This must be the inverse. So now we know that 28 is invertible, and we know the inverse of 28 has to be negative 35. It's the coefficient of the 28. But what's negative 35 mod 109? We'll just do it on your calculator at 74. So now you know the inverse. The inverse of 28 is 74 when you work mod 109. Check it on your calculator. You'll see that it's right. Example 4. In class, before we adjourned, we showed that 18 and 301 were relatively prime. And we reassembled 1. And it happened by 7 times 301 minus 117 by 18. So there's the inverse to 18. It's negative 117. So the inverse to 18 is negative 117, but that negative 117 is simply 184 mod 301. You can check it again. We're right. Here's a non-example. The very first example in class that we ever looked at of how to use the Euclidean algorithm showed that the GCD of 165 and 630 was 15. Well, 15 isn't 1. And so you also learn that 165 is not invertible mod 630. You check it on your calculator. Try to invert it. You can't do it. It's because they are not relatively prime. They clearly share a prime. 5 divides both. That ends in a 5 and that ends in a 0. They're not relatively prime, so one cannot be invertible mod the other. Okay? So here comes your first exercise that you're going to do in a Canvas reading quiz. So this is how I check your understanding. If you've been tracking with me, you should be able to carry this off. In the example we did above, which is that 12 and 77 are in fact relatively prime. So what I want you to do is I want you to do this by executing the Euclidean algorithm, and then you got to reassemble it. So once you reassemble it, that means you can write 1 as a multiple of 77 and a multiple of 12. I want to know what your multiples are, and I want you to use that fact to find the inverse to 12 mod 77. So the next thing in Canvas is a quiz that asks you to do that, and Canvas will automatically check your work for you. You can take that quiz as many times as you want until you get it right. This is how you learn. This would be like you asking me the same question in class 10 times until you understood it. That's fine. I don't care. If you get it wrong, try it again. There's no penalty. I will only record your highest grade. There's no reason not to ace this. Now, if you can't do it and you keep getting stuck, there's also a discussion board on Canvas. It's the link in the module. There's a link in the module to it. Just follow the module. If you have any questions, post your question to the Canvas discussion board on inverses mod n. I will answer it, or one of your classmates will answer it for me. This way you can get your questions answered, try the quiz again, get the quiz right, nail it, get 100%. If we do this, You will be able to learn this stuff remotely, and we're going to get through this course just fine. But this narrated handout is the replacement for me lecturing. You asking questions on the Canvas board is the replacement for you asking me questions in class to clarify or to go over something else again. And you taking the quiz proves to me that you've actually learned the material and that we can go forward and we can do labs, we can do homeworks and all the other stuff, okay? If you ever have any questions, let me know. The rest of this handout is just proving Theorem 1, that it is true that you are invertible if and only if your DCD is 1. You can read this yourself. I'm not going to read it to you, but this is just a proof of Theorem 1, okay? So I think you can do this because you already understand the Euclidean algorithm and Bezo's theorem. So try it, try it, try it. Get stuck, ask questions on the discussion board. Try the quiz. If you ace it, good. We'll move on to the next topic. I'll try to get the next topic up early next week. If you got any questions, reach out. Good luck. Take care of yourself.